Hi, everyone. So for our closing talk of this week, we'll have Jacques Tilouine, who will continue telling us about integral period relations for base changes.
Thank you. So last time we defined the congruence number as we defined the congruence number as basically T lambda of T lambda. Okay? This is the largest sub of T on which T acts by lambda, which is an ideal here. And then you apply lambda. So if M is a T module, finite flat, we defined eta lambda of M to be M lambda over M lambda. Oh, well, okay, sorry. We defined this as a congruence module, and this was isomorphic to O over eta lambda of M. In other words, this is the denominator of M lambda. So you have the property that M upper lambda times this number is equal to M lower lambda. We have seen that if we have a perfect pairing, which is so O perfect and T bilinear, we have eta lambda of M equal eta lambda of N. And also that this pairing induces a perfect pairing between M lambda and N lambda. This is perfect. And the corollary of this was that if you take a basis of M lower lambda and a basis of N lower lambda, then the pairing of these two elements was eta lambda of M. We have seen also that if we have two algebras with a surjective, I forgot to say this is surjective. So these are finite flat over O. We have a surjective homomorphism, and we have this thing. Then we can define a relative. So we have, of course, eta lambda 1. Okay, but we also have eta lambda 1 sharp, which I defined, and I prefer to define more general, which is eta lambda 1 of the module T2. And let me explain in general when you have M2 T2 module. So of course, finite flat over O. And a T2 module, we defined eta lambda sharp, so eta lambda 1 sharp of M2. So for that, we chose a splitting of T2 as T1E times T2 double prime E. And we considered, so I don't want to lose time. So we considered M2 theta, which is the sub of M2, the largest sub on which T2 acts via T1 through theta. So if you want a formula, this is M2 intersection 1 theta of M2E, okay? And on the other hand, you have M2 theta, but now you apply lambda 2, well, lambda 1, which is the same, because this is a T1 module. So you apply lambda 1. So of course, it is the same as applying lambda 2. And inside, you have M2 theta applying lambda 1. And the quotient is O over eta lambda sharp of M2. In other words, this is the number such that if you multiply M2 lambda 2 by this number, eta lambda 1 sharp of M2, you get M2 lambda 2. You get this thing, M2 theta lambda 1. Okay. So now comes so that we have seen, and we have seen also a factorization of the congruence number in this relative situation, namely that eta lambda 2 of M2 is eta lambda 1 sharp of M2 times, so something which is unfortunately not exactly what you would like to have, something like eta lambda 1. You get eta lambda 1 of some module which is M2 theta. So this is exact, but this is not exactly eta lambda 1. So even for the Hecke module, you don't have exactly the factorization like this. You have to modify this by eta lambda 1 of T2 theta, the largest sub of T2 on which T2 acts through T1. So that is correct, but this is only a divisor of the natural thing you could expect. And the formula of the equality holds in some situations when the rings are locally complete intersection, otherwise not exactly true. Anyway, now comes the key lemma. The key lemma is the following. This is how we prove some divisibility of period. So the key lemma is not here. Yeah. The key lemma is the following. So we have a perfect pairing M2 times N2 O perfect and a T2 bilinear. And we assume that we can find a linear form from M2 to O, so integral, okay, from this O module to this O module, which has the property that it vanishes on the non-base changes. Well, you extend it, now you can extend it to E, but it is integral, but you can extend it to E, and you take the part which is non-base change, okay? Then L vanishes. Then, this is the conclusion. Of course, you need to find such a L, but okay, if you have such an L, then the following happens. If you take something, some class, which is in M2 lambda 2, so in the sub of M2 on which T2 acts by lambda 2, then the relative congruence number divides L of C2. So this is the fundamental lemma. And of course, the conclusion is interesting if you find a C2 such that this value is relevant. Of course, you can take 0, but that's not very interesting. You need to find a good C2 such that this number is interesting. So, yeah, maybe I leave this. Well, I don't know. It's a short proof, but well, maybe I skip it. I don't know. Well, you want to see the proof? Tell me. Okay, so I give you the proof. So I start with the exact sequence which I wrote last time, M2 theta goes to 0. So this I explained last time. And we have this L, this linear form. This linear form, by assumption, vanishes on this. So this linear form factors through this thing. So you can view it as an element of the dual of M2 theta. The dual of M2 theta, we know it. This is the lower theta of the dual, because I explained that before. Well, there is a 2, but well, I forgot about the 2 here. Well, okay, yeah. Well. Okay, so L belongs to this. Now, if you compose L with 1 lambda 2, then this belongs by definition to n2 theta lambda 2, which is, as I explained, n2 theta lambda 1 is the same because on this T2 acts through T1 by, so it is the same. And now let's consider our element C, C2, somewhere, yeah. So C2 belongs to M2, and it is a 1 lambda, it is a 1 lambda 2 of something. So let's compute L of C2. This is a pairing between C2 and some element of this thing. So it belongs to this paired with N2 theta lambda 1. Or lambda 2, anyway. So there is a 1 lambda 2 here, but this is T2 bilinear. So it is the same as C2 N2 theta. I can keep the lambda 1. Well, okay, just a second. Yeah, okay, so let's say like this. But as I said, this is exactly eta lambda 1 sharp of N2 multiplied by N2 lambda 2 by definition of this quantity. Yeah, okay, here I forgot to say that this is the one for N2. Okay, this is obtained from this by multiplying by this quantity. So this is eta lambda 1 sharp of N2 multiplied by C2 paired with something in N2 lambda 2. But this N2 lambda 2 I can write as C2 N2 because the idempotent I can plug it in and here, and it does not act on C2 because C2 is already in the 1 lambda 2 of M. And now we have something in N2 and something in M2. So this is an integer. So this is divisible by this quantity. And that's it. So that's the key lemma, provided you find interesting L's. Now, how do you find interesting L's? Well, you go to the analytic automorphic form, the analytic theory of automorphic forms, and you look for period integrals. So period integrals are forms, let's say on L2, so we have LH goes to LG, phi, and we are considering L2 of GA over GQ, and we are looking for interesting linear forms which have the property that if an automorphic form belongs to a pi here, you have a number, P of phi, and if pi is a base change from H, this is always 0, and if pi is not a base change, if pi is not a base change from H, this is 0, and if pi is a base change, it is something maybe interesting. And there are plenty of those, these period integrals. And how do you construct? So P vanishes on pi if and only if pi is phi lower star of some small pi. So you need to find these linear forms. And actually, there are many situations where you have such linear forms. And actually, how do you build such linear form in the examples? You have to find another group H tilde. You are asking if a form here comes from there, and the answer is that the integral against this group vanishes or not. So the P will be integral. So this is a subgroup here. This is not a subgroup, okay? This is a base change. So you may not have a map. Here you must have a subgroup, okay? Such that if you integrate on HA over HQ times center of GQ by G dg, you restrict to H tilde. Well, this is the period integral, so period against H tilde. And so you have plenty of cases where you can find H tilde and where this is the discriminating, this is the answer. So let's give examples that we can consider. We will consider the case where H is GLN over Q and G is GLN over quadratic extension. F is quadratic, so real or imaginary. H is unitary, and G is GLN. Again, you have a notion of unitary over a real, for a quadratic extension, it could be real. But okay, let's say that F is imaginary quadratic. That's more to the point for us. You have the case of H being a GSP4 and G is GL4. You have the case where H is GL2 and G is GL3. So what is the map phi? So the map phi, so what is the L group? It is GLN, okay? So in the first case, phi is from GLN to GLN times GLN semi-direct product with one C. So C is the generator. This is the Galois group of F over Q. Here, same. Same, it will be GLN. Yeah, but the map is not the same. Okay, so what is the map here? It is the diagonal. This is phi. Okay, I am listing the phi's here. Here, the map is not the diagonal. Here, the map is G goes to G, comma, transpose G minus 1. Okay, here, this is the inclusion. Well, because I am identifying this with G spin 5, which is the L group. So this is the L group, but it is isomorphic to, canonically isomorphic to GSP4, which you can embed in GL4. And here, this is the adjoint, the adjunction, so adjoint. So here we will need to study adjoint of adjoint, okay, to GL3. And so these transfers have been established. So the existence of the transfer has been established by Arthur and Clausel. And not only they established that there exists a transfer from small pi to capital pi, but they characterized the image. And the characterization is that capital pi is equal to capital pi c. So if capital pi is equal to capital pi c, capital pi is a phi lower star is a base change. Here, the transfer has been established by Arthur and Clausel and Harris and Mock especially. So maybe I say Arthur and Mock. So you have the transfer. If you have a cuspidal automorphic representation here, you get, under mild assumptions, something cuspidal here. And the characterization, so the characterization is that it is a base change if and only if if and only if capital pi dual is capital pi complex conjugate, complex or real. So this has been established. Here, this has been established by Asghari and Shahidi, provided you start with some pi which is generic. If pi is generic, you have the transfer, and the characterization is that capital pi admits a Shalaika model. Anyway, there is a characterization. And here, this has been established by Gelbart and Jacques. And the characterization is that capital pi equal capital pi dual. Is add of small pi. So we have these cases of transfers. That's good. And we have H tildes in these cases. So what are the H tildes? So we have period integrals in these cases. So we will consider only, for the moment, only these cases, which give rise to linear forms L. So, so in the first case, one has to be careful. This is something I learned in a paper of Nadia Gurevich, that there is a strange duality between H and H dual. So if you want to find the H dual for this transfer, you need to use a unitary group. If you want to find the H dual for this transfer, you need to use GLN. Okay? And here, well, here, I don't remember. Well, I will talk about that later. So anyway, so for the moment, I will focus on these two. Okay? So the H dual here is a unitary group, and the H dual here is GLNQ. Okay? And so there is a name for these period integrals. So for the transfer from GLNQ to GLNF, the integral is called Jacques. So the P is the Jacques integral, and for the transfer from from UN to GLNF, P is called the Flicker-Rallis integral. So for the moment, we focus on this, and we define the P. So let's start with the simplest case, where actually we have a very complete result. That's the only case where the result is really complete. So this is GL2Q. Okay, we start with H to be GL2Q and G to be GL2F, so real or imaginary. So in that case, oh, this is okay. In that case, you find a class C2 in the. So what is yeah? So let's say F real first, quadratic real. Then we are so we are working with a Hilbert modular surface of level gamma 0n, something like that, and yeah, okay. With so the weight, as you know, is a pair of integers, the cohomological weight. So we will consider this, or O, of course. So the M2. So what is the M2? M2 will be this thing. So we start with pi on GL2Q. Okay, so and the transfer, as I said, has been established by maybe in that case it's Goy-Naganuma, maybe, but well, anyway, it's a special case of a transfer established by Arthur Clausel. So this is some Hilbert modular form. So we have the Hecke algebra. So something I forgot to say, that when you have this transfer, you have a map from the abstract Hecke algebra to the abstract Hecke algebra of H, which I denote by phi upper star. And it factors through HGS. So this is SG, if you like. We start with some pi here, pi on H. So it has some ramification locus, let's say S, SH. The base change will have the same ramification over F. So you have the corresponding ramification set here. So this map factors into a map at the level of the, so this is the cohomological Hecke algebra. The existence of this map is non-trivial. But if you forget about torsion, it's easy, it follows from the definition of the transfer using Borel-Wallach. But over the integers, okay, we are talking about the integers here, you need Scholzer representation. And yeah, it's not trivial, but anyway, you can define. So now you localize. You have a maximal ideal M. Here you have a maximal ideal MH corresponding to pi modulo P. And here you take the inverse image. So you have MG. You localize. So you have TG, which is the localization at MG of this one. And so these factors, that's not a problem. The problem is to show that these factors at the integral level here. If you go modulo torsion, it's okay. But you can do that under some assumptions. So you still have this thing. So you have this map. And so on the other hand, we have something I denoted in the old days, theta pi. Okay, I am changing again the notations. This is lambda. Now it becomes again theta pi. And this one, maybe it's capital theta. It was small theta. But, so this is the T2 goes to T1 goes to O in general. Okay. And so we consider M2, which is a TG module, which means the Hecke algebra for the Hilbert modular forms. Okay. Cohomological Hecke algebra. Here, yeah, well, okay. So that's the module we consider. You can localize if you like. You can localize. Does not change anything about for congruences, okay, or for periods. So so you have this, and what is the definition of the linear form? Well, you just make the integral cohomological. You have to interpret this map P, which is, so we are, well, yeah. You have to define P. So what is P in this context from capital pi to C? So phi goes to, well, you see, I said that there is this duality, but for GL2, U2 looks very much like GL2, except that there is a twist somewhere. And so I use GL2. So instead of saying that I will integrate over U2, I will integrate, or U11, I mean, I integrate over GL2 of Adels, modulo GL2Q times the center of AF. Yeah, yeah, if you like, AF cross, yeah. No, sorry, A cross, yeah, A cross. So instead of doing just phi of G, I have to multiply by beta of determinant G dg, where beta is a quadratic character of AF cross, or is a character of AF cross, is a Hecke character, which has the property that when you restrict beta to AQ, you get the quadratic character of F over Q. But this thing comes from the fact that I use GL2 instead of using U11. Okay, but okay, so you do that. You do that, and now you have to make this cohomological. How do you make it cohomological? Well, you consider this H2, and what you do is you use the restriction map. So this is a Hilbert modular surface, which contains a two-cycle, namely the modular curve over Q, so the GL2Q variety. So you see, in this context, I consider GL2Q base change to GL2F, and I use GL2Q for the integration. Okay, this is my H tilde. So what I do is to consider the restriction. So I restrict to H2 of the modular curve. So the classical modular curve, this is over Q. This is, if you like, this is over F. This is over Q. And you restrict this sheaf, and this sheaf becomes a tensor product of the sheaf Vn and the sheaf Vn. And now you use the pairing, which is basically self-dual. So you use the pairing here, you use the integration, and you go to O. So if you like, you go to H2 of YO by pairing these two things, and then this is isomorphic to O. You need to consider compact support, of course, but we localize at a non-Eisenstein prime. So this is equal to that. Okay. You can put compact or not, because we localize at non-Eisenstein prime. So we kill the boundary cohomology. So that's the definition of L. So this is our L, composition of all these things, which is a cohomological interpretation of this integration. Well, you will tell me that there is this twist, so actually you have to go to the discriminant, you have to add some level. Yeah, well, there is, okay, some detail, because you need to introduce this character, but that's a detail, which I skip. And so what happens, this is the beautiful calculation of Hida, which is that we need to take a nice class. So which class do we choose? We choose the image by the Eichler-Shimura map iota2 of the normalized Whittaker function, if you like, or associated to pi. And we divide by the period. So here it depends on epsilon, because, yeah, I'm sorry, this is not rank 1. So, yeah, we need to take the epsilon part. You choose some epsilon, a character. So epsilon is a character of plus minus 1 square, because we are over a quadratic extension. So, character of this. So we took iota2 epsilon of the nice automorphic form that we chose. So we have a period, which is omega capital pi 2 epsilon, where 2 we drop. And this, as I said, is a basis, okay, of M2 lower lambda. This is our C2. So we apply L to this, which amounts to calculating the integral of phi of G twisted dg. And this is with this space here. And this calculation has been done by Hida. And the result is that you find L of adjoint rho pi tensor by alpha at 1 and divided by these periods. Divided by this period, omega 2 epsilon. And this is very nice because this is exactly the motive we are interested in. If you remember, in this context, the datum of phi gave rise to a decomposition of the semi-simple part of the Lie algebra of the dual reductive group as semi-simple part of the Lie algebra of H plus something. This is valid over O, okay? And in the particular case we are, here we have SL2 plus SL2. This is the Lie algebra. I remind you that LG is GL2 times GL2 semi-direct product 1C, okay? So if you go to the semi-simple part, you get SL2 plus SL2, and here you will have, of course, SL2, and I remind you that the embedding is diagonal here. This is phi. Phi is diagonal. So here you will have another SL2, but anti-diagonal. So this is SL2 diagonal, and here SL2 anti-diagonal. And I remind you that there is an action of the L group. This is the adjoint action, but there is a Galois representation. And if you compose, this Galois representation is ad rho pi, and this Galois representation is ad rho pi twisted by alpha. So I had a notation which was that adjoint of rho capital pi is equal to adjoint of rho small pi plus another Galois representation or another motive. So this motive is this one. So this is the motive we are studying. And so we are lucky, we find exactly this motive, this L function by calculating L. Now, here is the proof. Now let me give the proof of our theorem, which I haven't stated, but I will state it. So this is the theorem with Eric Urban in 2022. So this is half of the theorem. But this is the relevant part for these talks. So our theorem is that, well, I defined for you omega pi, omega adjoint rho pi. It was omega pi epsilon, omega pi minus epsilon. I defined for you automorphic. I defined for you this one, and that was omega pi plus omega pi minus. And now there is omega x pi automorphic. So we define it to be omega pi epsilon. And then we define it like that. And so what we prove is that we have perfect decomposition as expected. So this is exactly up to unit, omega add rho pi automorphic times omega x pi automorphic. And so the conclusion is that we have a Bloch-Kato formula for this motive, namely that this divided, well, not exactly Bloch-Kato, this is the automorphic counterpart. The conclusion is that this divided by this thing is exactly eta lambda sharp, eta theta, eta pi sharp. Yeah, so that's what we prove in this real case. So this is the conclusion, okay? And this plays the role of the automorphic period. Well, there is a subtlety. Epsilon, you have 4 choices, but actually there are only 2 which are allowed, namely those such that, so epsilon is a character of plus minus 1 square to C cross, and there is a condition on epsilon, it cannot be any character, it must satisfy epsilon of -1 equal -1. We call this epsilon balanced, and epsilon has to be balanced. So there are only two choices. Okay, so we find we find this. So this is the real case. But yeah, so this is a conclusion. But this conclusion involves two, as you see, these numbers. To say that two numbers are equal, you have to prove two divisibilities. And actually, our technique of linear forms prove only one divisibility, namely, so we prove this, but we have two completely different arguments. The argument involving the linear form proves only this divisibility. Eta pi sharp divides L x pi 1 over omega pi epsilon. So this one is via L, via the linear form. The other divisibility we prove by using Cornu-Vatsal, and it works well, but we cannot generalize this argument beyond GL2. So for GL2, we do prove this. This is via L, and the other divisibility is via Cornu-Vatsal. But okay, so anyway, we prove this. So in the imaginary quadratic case, it's nice. Also, we have a perfect formula also. One by Cornu-Vatsal, one divisibility by Cornu-Vatsal, and the other by some L. So the L is just the same. So I don't do the detail, but so for F imaginary quadratic, well, the L is similar. You restrict. You see, you have a variety of dimension 3. So the relevant cohomology is H1 and H2. We consider H2, so H top. We consider H2 of the Bianchi variety. So YG is the Bianchi variety with coefficients in V and N again. We localize, and the linear form so starts from H top, not H bottom, but it is the same. Okay, so you restrict to H2 of the modular curve inside this threefold. So it's a two-cycle. So you go to this, well, you put compact support, but it doesn't matter. VNNO, and then this becomes again Vn tensor Vn dual, if you like. So you pair that and you send to O by integration. That's the linear form. And you have again a formula of Hida, the same formula. So again, you consider iota 2, so the Eichler-Shimura top of the Whittaker function normalized, divided by omega 2 pi. This is the base change. And you get this is the C2, okay? And you get L adjoint rho pi tensor alpha 1 divided by omega pi 2. So the difference between imaginary quadratic and real is that this value is not critical, while this value here is critical. So this is again, for the same reason, this is again my x pi. Okay, this is again my x pi. So this is again, so this strange period is the omega x pi automorphic. We are dealing with a non-critical value, so we have a non-critical period, and that's the one. And again, we prove that this is correct. So we have Lx pi 1 divided by omega pi 2 equal exactly eta pi sharp. So this requires the theorem of Caligari-Gherati, because a priori what you get is eta pi of M2, which is eta pi of M2 by duality, but this is eta pi sharp because this is free, and that's a theorem of Caligari, free of rank 1 over T2, Caligari-Gherati, over T2 by Caligari-Gherati. So So this formula is true. But again, the relevant part for this study is the divisibility. This divides that. The other one is via Cornu-Vatsal. So we have this perfect formula. So if you want to a more concrete, yeah, well, anyway, that's enough, maybe. That's enough for GL2Q. So for bigger groups, so what is the strategy? The strategy is very similar. So what do we do? So let's go now to GLN. Let's consider GLNQ to GLNF, quadratic. Let's say imaginary. So same notations. We will have a decomposition of add rho pi 1 equal L add rho pi 1, L add rho pi tensor alpha 1. So that we have, same reason, okay, the same calculation like here, okay. This is for GLN. So what we do is we divide this by omega pi epsilon, so maybe omega pi bottom epsilon, or maybe not epsilon, because I said I consider an imaginary quadratic field, so there is no epsilon. So omega pi bottom, omega pi top. Here I have omega pi bottom Q and omega pi top Q. So maybe this is bottom F and top F. And here, well, here for the moment, I consider the quotient, okay? Q is defined to be this divided by that. Then you cannot complain, okay? So, okay, but now we use the theorem of Balasubramanyam Raghuram. This is eta capital pi. Well, there is, so for the moment we assume the conjecture. A priori, there is a C infinity F to get this. And here, similarly, there would be a C infinity Q to get that this is exactly eta pi. So we assume these are p-adic units. We can prove that they are p-adic units for GL3, but okay. So GL3 Q to GL3F works. So we have this, and here we have something, maybe L pi, which I don't want. This is the quotient here. Okay, now this is an equality. Now I use the divisibility that I mentioned before. This divides eta pi times eta pi sharp. Okay? But okay, of course, this is eta pi of M2. M2 will be H top. Yeah, well, okay. H top of YG V lambda G O localized at MG. Well, you should answer. Okay, so eta pi of M2. So this is eta pi of M2. But when I say M2, I could say N2. Okay, it's dual. But M2 or N2. So we have that. Now, well, let's say N2. Now we use the key lemma. And the key lemma, in this context, again, by using Jacques integral, tells you that this divides L of C2. So of course we choose C2 to be iota top F of phi divided by omega pi top F. So this one, so we have, so this product divides eta pi small pi M2 or N2. Yeah, so here we really need that this is eta pi. I'm sorry. Yeah, so have to be careful. Yeah, divides maybe. Divides because this is the Hecke thing, okay? So the Hecke thing is a multiple of, okay, so we get this, an eta pi of, and eta, oh, no, eta pi times this, yeah, this divides this, okay? Now this, when you compute, is the adjoint L tensor alpha divided by this period. And so, so you are done. You get the divisibility that, you get the divisibility that this quantity divides this quantity. In other words, 1 divided by Q divides 1 divided by omega pi top. And this implies that you get one divisibility, namely omega pi top times omega pi automorphic. So the conclusion is that you get one divisibility, and you think that this is an equality. So omega automorphic add rho pi, omega add rho small pi automorphic, you get this divisibility. And so the conjecture is that if you assume that rho pi, of course we assume that rho pi bar is absolutely reducible, but you assume even that it satisfies the Taylor-Wise condition. Minimality, okay, minimality, then the conjecture is that this should be an equality. And we can prove one divisibility, and for the moment, we don't see how to prove the other one, because Cornu-Vatsal does not generalize for the moment to GLN. But so we conjecture this, and we prove this one divisibility. And so I may stop. So anyway, you see the idea of the proof. This is exactly the idea of the proof. This is an equality. Here, this is exactly this. This is exactly, well, this is something which divides this. So you have this divisibility. Here I copy, so I don't change anything. But this number, I know that it divides this product. And this, I use the key lemma. And the key lemma tells you that this quantity divided by something else, okay, is a multiple of this. So you get 1 over Q divides 1 over this, and therefore you get this divisibility. And that's the, well, this we can do also for GSP4 in a joint, also this is a joint work with Baskar and Balasubramanyam. We use AI to compute the constants, which so for GL3, we can prove that these are units. And so, yeah. So for GL3, we do have the divisibility. Otherwise, there are some conjectural quantities here and there. And so we do the case of GSP4 to GL4 with Kartik Prasanna, and we have one divisibility also. And we do also the case of the base change from UN to GLN. But this is, so to be frank, this base change to GL3F, we can do only for n equal 3. We cannot do it for larger n. This one, if we knew that you have units, we can do in general. This one, no, okay? Yeah. Only for 3. And for GSP4, we have a similar divisibility. So I didn't mention that the Lapid-Mao conjecture that we use for GSP4 is a theorem of Chen and Ichino. So the fact that if you start with a Siegel modular form, which is, so on GSP4Q, which is generic, the fact that this value is related to the Peterson product of the generic form in pi is a theorem of Chen and Ichino. And we need this starting point to, well, because we need this kind of formulas And then, so what is X in that case? This is interesting. So here you will have, so this is SL4. This is SP4. And this is, so dimension 15, dimension 10, dimension 5, and this is the so-called standard representation. So this is a representation, of course, of GSP4. So it's a representation of GL4, but I restrict it to GSP4. Okay, so this is a GSP4 decomposition for the adjoint action, and this is a representation of GSP4, which is through the orthogonal group O5. You see, you write GSP4 equal G spin 5, and then you project by this standard representation to O5. Basically, G spin 5 divided by center is O5, and then O5 is contained in GL5. So this is called standard 5. So that's the 5-dimensional representation which occurs here. So this is the X. So our theorem is about L of this divided by some period that we find. Okay. So in that case, that's the motive. This is our X in the GSP4 case. And to be frank, this is the hardest of all. GL2 to GL3, we cannot do that. We tried hard, this adjoint representation. We couldn't find the period integral. There is a period integral, but it involves the metaplectic group, and the metaplectic group is not algebraic. So you cannot find a variety associated to the metaplectic group. You cannot consider the cohomology of this variety. So we don't know how to make the integral a linear form over cohomology. So this one we cannot treat. Although we have a conjecture, but we cannot prove it. This one, yeah. But the other ones, we prove at least one divisibility. And I stop here. I started early, so yeah, I stop here. Okay.
Any question? I have a very basic question.
Sure.
So earlier you're looking at this with there's the real quadratic case and the imaginary quadratic case.
Yeah. Or GL2?
Yeah, and you had like your linear form and your Cornu-Vassal for the two different divisibilities.
For one divisibility, we use Cornu-Vassal, and for the other, we use this linear form.
Right. So, very basic question, but like, are you using Cornu-Vassal because there's some kind of obstruction to using a linear form again, or is it just faster?
No, it's very interesting that it's, you know, we are studying the adjoint L, okay? We are studying this kind of value. But Cornu-Vassal, let's say with the classical modular form, okay? We are studying this, but Cornu-Vassal is something about L of F tensor characters 1 or some value, K minus 1, something like that. And the key point is that this tells us something about the periods. Okay, there are periods here, which are omega F plus or minus, okay? But Cornu-Vassal tells you that you can adjust this to be a unit, p-adic unit. And because of this, you get a divisibility of periods, okay? And this one is the other one from that. It's very strange because you see these L functions have no relations, but using this we prove one divisibility, but using this L function we prove another one. And this philosophy, I don't know how to generalize. We need the theorem that this kind of value can be made a unit, p-adic unit, and this will give you a divisibility.
Any other questions? Okay, let's thank Jacques again.
So as I am the last speaker, I would like to thank the organizers, the staff. Everything was very smooth. And so I enjoyed the conference. I hope you too enjoyed. So let's thank the organizers. And the staff, of course.